Hello everyone. We are excited to present our project on adversarial, robust and accurate machine learning for image classification. This research focuses on strengthening AI-driven medical imaging systems against adversarial attacks that can manipulate diagnostic outcomes, ensuring more reliable and accurate results. We are Yugendran, Muthividiraj and Akash, students from EC department, representing Welltech Multitech Dr. Rangarajan Dr. Sakuntala Engineering College. This project has been carried out under the guidance of Mr. A. Mohammed Abbas. We sincerely appreciate the valuable insights and continuous support throughout our research. We look forward to sharing our findings with you today.
Abstract: Enhancing accuracy and security of medical image classification against adversarial attack. Medical imaging has revolutionized healthcare, there's no doubt in that, enabling doctors to detect diseases with remarkable accuracy. But what if I told you that these systems can be tricked by invisible modifications to images? This is what we call an adversarial attack. This may be a manipulation of that image or adding some noise to it. In this video, we'll explore the vulnerabilities of machine learning in medical image classification and our proposed methods to enhance security and accuracy. The average accuracy of a model is 88.8%. In addition, different models have different tolerant abilities on adversarial attacks. Basically, the first image, which is a panda, as you can see, is attacked with a noise. This noise manipulates the machine learning algorithm to, to identify the image as a gibbon, which is a variant of panda. Problem statement. Machine learning models, especially in medical imaging, are vulnerable to adversarial attacks. Small but often invisible changes to the data that cause models to make incorrect classification. This susceptibility poses risks in critical areas like medical diagnosis, where accurate predictions are essential. Literature survey. We have taken three papers mainly. The first consists of reconstruction of images. The second is a noise cancellation and identifying high sensitivity points. The third is hop skip jump algorithm. This is the architecture. As you can see, the input image is given to the dataset. If an attack is found, we just verify it with our algorithm and, and it goes on. Black box attack. There are mainly two types of attack, which is black box and white box. We'll go ahead first with black box attack. The attacker in black box attack, the attacker has no direct access to the model's internal workings, but manipulates the input images based on the output predictions. However, it is hard to practice on networks in the real world since the massive queries to model are time consuming. It also achieves competitive performance in attacking severely widely used defense mechanisms. White box attacks. Unlike black box attacks, white box attackers can access all the information of the target models, such as architecture, parameters, and gradients. Therefore, the white box attacks can carefully craft adversarial example by using this crucial information. Recent researches on aim to help people understand the weakness of DNN models. Fast gradient sign method (FGSM) and projected gradient descent attack will be used in this discussion to study the defensibility of models. Proposed method. To combat these attacks, we propose a robust multi-model approach. Our framework consists of three key techniques, which is dual path residual CNN or DPRCNN. Second, random depth-wise CNN, which is RDCNN, and sign activation networks (SCD). A major focus is on SCD, but we'll explain the first two steps. Dual path residual convolution neural network. This combines MRI and pathology images of brain tumor classification. Utilizes ResNet architecture with two input paths. Achieves 85% approx validation accuracy when combining tumor segmentation and pathology images. So the next method is random depth-wise convolution neural network. uses random convolution filter to learn unsupervised features. This outperformed resonate with a 95% average accuracy on medical databases. Our main focus is on SCD due to its accuracy and robust works. Sign activation networks, or SCD, stochastic coordinate descent, includes SCD-01MLP, SCD-SCMLP, and SCD-CEBNN to resist adversarial attacks. Achieves approximately 89% accuracy on adversarial example, surpassing traditional models. Adaptive image reconstruction. Proactively defends against attacks by applying entropy-based noise removal. This achieves detection accuracy of 97% in MNIST and 92% in ImageNet. Software which I'm using is MATLAB version R2002B. Well, this is the example. We'll show you an example in the MATLAB in the further thing.
First, navigate to your desktop and open this PC. Next, double-click on the C drive. Inside the C drive, locate and open the user folder. Now, find user profile and click on it. Inside your user folder, locate and click on the OneDrive directory. From here, open the desktop folder. Within the desktop folder, find the attack folder and double-click to open it. This is where our images are stored. Once inside the attack folder, you can now select and import the required images. In this demonstration, we will explore a method for removing adversarial noise from medical images using an advanced denoising approach based on Charlotte principle. The technique applies interscale orthonormal wavelet thresholding to effectively reduce noise while preserving critical image details. Now, let's break down our MATLAB code implementation step by step. We begin by loading a medical image and converting into a grayscale. To ensure uniform processing, we resize into 256 into 256 pixels. We introduce artificial adversarial noise to the image. The noise follows a Gaussian distribution with a standard deviation of 20. This stimulates real-world adversarial attacks that can alter medical image classification. Now, we apply the OWT-Charlotte denoising algorithm. This method removes noises while preserving important features in the image, ensuring that critical medical details are not lost. To evaluate the effectiveness of our denoising method, we calculate the peak signal-to-noise ratio (PSNR). A highly PSNR value indicates better quality restoration. We compare the PSNR before and after denoising to measure improvement. Finally, after completing this code, we have to run the program. Yeah, finally we visualize the result. First image is the original medical scan. The second image shows the adversarial attack version with noise added. The third image demonstrates the denoised output, where adversarial noise has been successfully removed. The PSNR improvement confirms the effectiveness of Charlotte method is restoring the medical images. To summarize, our method effectively removes adversarial distortion from medical images while preserving important details. This ensures more reliable AI-based diagnosis and enhances security in medical imaging applications.
This discussion presents three neural network frameworks with higher classification accuracy than state-of-art models. A novel adaptive image reconstruction defense mechanism is proposed to address this misclassification caused by defense schemes. To sum up, our research enhances the security of medical image classification against adversarial attacks using advanced deep learning techniques. By integrating robust models and adaptive defense mechanisms, we significantly improve the reliability in critical applications. So this is our presentation on adversarial attack on medical images. Hope you understood. Thank you.